write down the Hamiltonian describing now weakly interacting Bose gas. We write down non-interacting part. And now we write down in a second quantized way part related to interaction. So it's A dagger K2 minus Q, A dagger K1 plus K2 plus Q, A K2, A K1, and here it's Q over. And summation is taken K1, K2, Are you familiar with this form of the Hamiltonian? So A are creation and annihilation operators subject to bosonic statistics. Here, the quadratic part, it's just energy and epsilon k is equal to h squared, k squared over 2m. And this is pairwise interaction of particles, which, as I said, is visualized as a short-range interaction. Particles interact when they only collide, so they act like four hard balls. And what is written here is that particle with a momentum k1 minus q comes and collides with the particles with a momentum k2 plus q. They interact. Let me put interaction as a wavy line. And as a result of scattering of these two particles, collision, the momentum q is transferred, and particle k1 minus q scatters, being characterized by momentum k1, and particle k2 plus q release the momentum and have a momentum k2 at the final step. This is the simplest Feynman diagram, so to say, describing this process of scattering. But you should not now think about the language of Feynman diagrams. This cartoon has a very simple meaning. As I said, two particles, two objects collide. The momentum and energy is transferred. This is the initial state of two particles before collision. This is finite state of two particles after collisions. As I said, only two particle collisions are taken into account. Of course, it's natural to confine our Hamiltonian by this term. Why? Because any kind of higher order collisions, for example, where three particles collide, are less probable in dilute system. So when the density of particles, you have a gas, is so dilute, then the probability to have three particles coming together at some point are much smaller compared to probability of only two particles to collide. Therefore, all processes, higher processes, have to be disregarded. So this is the simplest Hamiltonian. And as I said, if we recall a little bit of collision theory, we may say that this potential Q, its Fourier transform over potential minus IQR dr. And as I said, potential exists only on the distances of the size of the particles. Therefore, we can say that potential is very short range and characterize it h squared a over m with a scattering length a. and the approximation of weak interaction, you see the A replaces potential. The scattering length is a new parameter which is equivalent to the strength of interaction. And in order to say that we are in the regime of weak interaction, I'm repeating what I have said. We have to say that the A, the scattering length, and the scattering length is of the order of the size of atom, which is angstrom size. A should be much smaller compared to the main distance between particles. The mean distance between particles is a density to the power 1/3. Therefore, we write down that n to the power 1/3 A is much smaller than 1, or A n A cube is much smaller than 1. Sometimes this parameter is called gas parameter, so we are in fact in approximation of the gas. I don't know whether you discussed it or not, but if we think about electrons, which are, by the way, charged particles, then the gas approximation will be completely different. What does it mean to have a gas approximation for charged electrons? First of all, we need to say that in gas approximation, the typical kinetic energy, which is, say, p squared over 2m, which is m a squared. So this is a remark about electrons. Should be much larger compared to potential energy of the interaction. This is again quite natural idea to say what is weakly interacting system is. The potential energy is much smaller than kinetic energy. But potential energy of interacting electron comes mostly due to Coulomb interaction. So this is E squared over A. So we may write down that E squared, m E squared over H squared A is much smaller than 1. What is typical A in this formula? We have a fermionic system, and typical coordinate is inverse Fermi momentum. So A is 1 over Pf. Right? What is this H squared over m E squared? Do you remember? This is a Bohr radius of the hydrogen atom. So in fact, we can rewrite this inequality as Pf A Bohr is much larger than 1. You remember from our first lecture that Fermi momentum is proportional to the density to the power 1/3. Therefore, we have A Bohr cube n is much larger than 1 for the system. To contrast with this one, if there is any contradiction, no. There is no contradiction. In fact, the system characterizes charged particles. The Coulomb behaves as 1 over r. Therefore, in order to suppress effect of interaction in charged system, one has to have high density. Therefore, metals are good metals when this condition is fulfilled, and this is fact true. Then the Coulomb interaction is screened. So if you have a low density, then metal becomes bad and bad, worse, and at the end of the day, you come to something which is known as linear crystallization, for example. Lowering density in a fermionic system leads to dramatic effects associated with losses of metallic properties and tendency to be insulating. So, Bose gas contact interaction, short range interaction. This one, Fermi gas, becomes more and more ideal when the density is high. Okay. Let's write the total number of particles. N is equal to N node plus sum over K not equal to 0, A K dagger A K. So here I put the operator of the total number of particles, and its eigenvalue is characterizing the number of particles in the system. Of course, when only diagonal part is concerned, let's put U equal to 0 for the moment. Then, what energy is the quantum mechanical mean value epsilon k, a k dagger, a k, k not equal to 0, and k, which is then the formula which we used, which is epsilon k and k average, k not equal to 0. However, if u is not equal to 0, what we have here, we have two creation and two annihilation operator, and in order to calculate energy, we need to diagonalize this Hamiltonian to bring it to quadratic form. So this is our goal, and this is what we will be doing for some minutes today, and start the day after tomorrow. In order to do it, let's see that there is macroscopic number of particles occupying state characterized by zero momentum. So this is condensate. So although these are operator, this is a number. And this number, and node, is much larger than 1. As I said, we will be doing now calculations for temperatures smaller than T node, and N node is equal to N 1 minus T over T node to the power of 2½ Then the smaller temperature is, more particles are in the condensate, and at temperature equal to 0, this number coincides with the total number of particles, and N is, of course, is macroscopically large, is 10 to the power of 23. So you see that even temperature is not too small compared to T node. We still have very large number of particles sitting in the condensate. Therefore, we can say and introduce operators characterizing creation and annihilation of particles, bosons, in the state k equal to 0, and we can say that A node is of the order of square root of N node. It's just C number, and A node square is of the order of N node. So N node itself is A node dagger A node plus sum over K not equal to 0, A dagger K, A K. So then we have to look into this Hamiltonian and identify the processes when two of the momentums are small or equal to 0, and see what is the contribution of these processes to the Hamiltonian. So at this very moment, we start doing some approximation. Namely, we classify processes and eventually drop all the processes involving particles, both particles being out of condensate. We will take into account only the processes where one of the particles which scatters on another particle is in condensate while another one is out of condensate. So first of all, let's discuss the only process where both particles of scatter are in condensate. So both in, which means K1 is equal to K2 is equal to Q is equal to 0. So then H interaction 1 is equal to what? Is equal to 1/2 U node over V, and times, since each creation and annihilation operator is equal to a node or a node dagger, then this is n node squared. This is just a constant which describes us the origin of the energy. So this is a constant shift of energy. So then, let's, as I say, discuss the processes where only one particle is in condensate and another one is out of condensate. There are several kinds of processes of that sort. For example, if K1 is equal to K2 is equal to 0, but Q is not equal to 0, then H interaction 2 is equal to 1/2 sum over Q, UQ over V, A dagger minus Q, A dagger Q. So K2 is equal to 0, K1 is equal to 0. We replace this by n node, and these two remain on 0. As I said, at this very moment, I will assume that my potential is very short range, and everywhere I will replace U, Q as approximately U0. So therefore, this one is equal to 1/2 U0, and node sum over Q, A dagger minus Q, AQ. However, since you need to understand my calculations, and the best way to understand calculations is to repeat them yourself, my suggestion is repeat my calculations, not assuming them, namely keeping UQ as a function of Q. So keep it up to the last stage of calculations, and you will arrive to the formula for energy a little bit different than my formula. The reason to do it is to consider, at the end of the day, the situation with the charged bosons. Suppose you have charged bosons, like fermions, which we discussed now. Suppose they are interacting by means of Coulomb interaction. Then we know that for Coulomb interaction, it's not the case of short-range interaction I'm discussing now, namely unscreened Coulomb interaction in three-dimensional case behaves as 1 over Q squared. Namely, it's singular for small q. But if you will repeat my calculations in correct way, keeping q in points where one needs to keep q, one can come to very interesting formula for the dispersion of charge Bose gas, which we will also discuss in one of the tutorials. Okay, situation number 3. I'm just listing all possibilities to have 2 of momentums equal to 0, while the third one is not equal to 0. For example, k1 minus q is equal to 0, and k2 plus q is equal to 0, which means k1 is equal to q, and k2 is equal to minus q. So then, k1 minus q is equal to 0, k2 plus q is equal to 0, H interaction 3 is equal to 1/2 U node N node sum over Q K2. Minus Q A. Okay? So you see that interesting property of these two contributions, but both of them are proportional either to creation operator or to annihilation operator. Therefore, when we will diagonalize this part, we will need to get rid of these combinations and come to new quasi-particles. Okay, the last thing which I will be able to do today is probably to finish classifying all the processes. So now I'm listing processes of the fourth part. These are processes of that sort. K1 minus Q, for example, is equal to 0, but K2 is equal to 0. A. Or process B, K1 is equal to 0 and K plus 2 is equal to 0. Or C, Q is equal to 0, K2 is equal to 0, or D, Q is equal to 0, K1 is equal to 0. So if it is like that, it means that one of the creation operator is replaced by square root of a node, and one annihilation operator is replaced by a node. For example, H interaction for A is equal to 1/2 U node N node over V, sum over K. As I said, K1 is equal to Q, K2 is equal to 0. So this one remains A dagger K, A, K. And all the rest for B, for C, for D will be the same. Unlike the processes shown here, where there are two creation operators or two annihilation operators, this part of Hamiltonian is already diagonal. If we collect everything in one expression, and, as I said, neglect all scattering processes which involve both particles being out of condensate, then we can write down that H is equal to E node, and this is E node, constant, plus sum over K, epsilon K plus let me just be not so much in a hurry. 4 times 1/2 U node N node A dagger K and K plus sum over K U node over V N node, and here is 1/2, and here A K dagger A minus K dagger. Since the separator commute, it doesn't matter in which order I put A minus K, A, K. Okay. The only point is here. As we discussed, the chemical potential below the temperature equal to 0 for non-interacting gas is 0. For interacting, it is not. But still, the number of particles in the condensate and out of condensate itself is not well-defined quantity. Therefore, I need to replace a node by n. But when I do it, I need to be careful. Namely, I wrote that n is equal to a node plus sum over k not equal to 0, a dagger k, a k. Therefore, a node squared is equal to n minus sum over k not equal to 0, a dagger k, a k. Square, this is n prime, and since I'm interested in the situation where n prime is much smaller than n, I should write it as n squared minus 2 times n sum over k not equal to 0, dagger k, a k. So I ignore n squared term, and now let me do the following. This n node square comes into E node. I would like to write E node in terms of n. Then the total number of particles is there, and I'm guaranteed that this is a well-defined quantity. So you see that the difference between E node and E node tilde is that n squared and n node squared should be in one and another expression. So if I put a node square here, then what I see, the additional term with minus 2n, which will then come and change me the number of particles there. You see, it's twice u node over v, n squared. So what I do now is to put 2 times here, and there, because it's exceeding the accuracy if I will plug in this formula. So since this is already processed, including one particle in condensate and one in other condensate, I can replace n node by n everywhere except here, and here I subtract the combination which comes. So E node now depends. So if I introduce shorthand notations, namely, let me introduce beta equal to 1/2 u node over v times n, and psi equal to epsilon k plus 2 beta, then my Hamiltonian can be written as follows. So it is epsilon node plus sum over k not equal to 0, psi k, a dagger k, a k, plus beta sum over k not equal to 0, a dagger k, a dagger minus k, plus a minus k, a k. So this is a Hamiltonian I'm going to deal with next time. You see that this is quadratic form. The Hamiltonian is already quadratic with respect to creation and annihilation operators. But it is not yet diagonal because it contains this off-diagonal combination. What I have to do, I have to rotate this Hamiltonian to introduce new variables and adjust my rotation such a way that in new variables this Hamiltonian is diagonal. And this rotation is known as Guadalupe transformation or UV transformation, and this has very influential, it plays very influential role in calculations of spectrum of the Bose gas. And we will see that this Bogoliubov transformation has a lot of implementation in other fields. So as I said, my goal, what I will do next time, is to write down this Hamiltonian is some u epsilon k b k dagger b k, k not equal to 0. So I need to find the following: what epsilon k is, and how operators b, k, which are bosonic operators, are connected with operators a, k. And as soon as I do that, I'm working with the quasi-particles, and my Hamiltonian is diagonalized in terms of the quasi-particles. I can implement all power of theory of non-interacting gas, but the question is how this energy depends on the limit. I will stop here for today, and on Wednesday we start with this Hamiltonian and proceed with diagonalization, and then discuss the properties of this weekly non-ideal Bose gas. Questions? So if not questions, then that's all. Then probably I have questions. I'm teaching this course here for the first time. I did different courses of that sort in different places, but in principle we have two options. I will finish what I plan to say within, say, 14 or 15 lectures. So there will be 3 or 4 remaining lectures which we can spend in a different way. For example, the one option is to teach you a little bit the green function formalism, and how to use and how to construct many-body perturbation theory, and what the green function is, because this is a very powerful tool to proceed with the calculation. It has a lot of meaning from the point of view that poles of green function describe the energy of excitations, while real part of the pole, while imaginary part describes the damping. So one can discuss these issues which I have already touched upon on previous lectures in terms of very nice and simple formalism. But of course, in order to approach to this point, one needs to learn something. This is one option. Of course, in tutorials, my assistant will show you connection and appearance of green functions in the theory of linear differential equation on 2 examples, namely when the scattering theory and Schrödinger equation is discussed, one thing, and when the Bloch equation describing behavior of spin in a magnetic field, in time-dependent magnetic field, on another side. So you will anyway learn what ordinary green functions are, the green functions as a solution of linear differential equation. However, the many-particle green function is a subject which we may possibly discuss in a few lectures here. Another option completely different to that, we forget about green functions and discuss kinetical properties of solid states, namely Boltzmann kinetic equation and transport through the systems. Again, in 4 lectures, I will be able to give you basics of theory of kinetical theory in application to solids, explain what collision integral is, and explain some properties. I am not yet decided. So if there is any strong opinion towards one or another direction, please let me know. If no, then I will see how quick we proceed with the main course, and then in the process I will decide it. But I invite you for this discussion. Okay, that's all for today. I'm waiting for your questions, and we meet Wednesday. No, I take the integral. First, look. Here I put temperature equal to 0. If temperature is equal to 0, this function, which is written here, it's just a step function. So previously it was function of that sort, and integration was till infinity. But at temperature equal to 0, I replaced it by, so if temperature equal to 0, then e to the power epsilon minus mu over temperature plus 1 is equal to theta function over epsilon minus mu minus epsilon plus mu. So, minus epsilon plus m, which theta function x means that it's equal to 1 if x is positive and if x is negative. So here, if therefore minus epsilon plus ef is positive, then it is equal to 1, which means that epsilon is less than Fermi energy. Therefore, I replaced it by the step function, and therefore it removes from, and therefore I replaced Fermi energy, became potential by. So this is how the Fermi distribution function is defined. Then I calculated this integral. It's not a big deal. It's this 3/2. You see that integration over energy was from 0 to infinity. When I put a step function, this condition provides me that this is Fermi energy. Okay? So this is how Fermi energy is. But on the other hand, the argument of the square root should be positive. So it defines me low bound in the energy. So therefore, epsilon minus h omega c n plus 1/2 should be positive. Therefore, epsilon is larger than h omega c n plus 1/2. So if summation comes here, then I write h omega c n plus 1/2. Or this is the same. And here it's integral of epsilon. So I put square root over 2n here. Epsilon minus h omega c n plus 1/2 to the power 1/2 d epsilon. So this integral, I continue. It's square root over 2n, sum over n. So it's 2/3 epsilon minus h omega c n plus 1/2 to the power 3/2, right? This is how I calculate integral. And now I have to put limits. H omega c n plus 1/2 Fermi energy. In the lower limit, since this is a condition of square root, it is equal to 0. For upper limit, it is equal to Fermi energy. So this is 2/3 square root over 2n, sum over n, EF minus h omega c n plus 1/2 to the power 3/2. But summation over n is also limited because this argument has to be positive. So now EF minus h omega c n plus 1/2 is positive. Therefore, n is smaller than Fermi energy over h omega c minus 1/2. But Fermi energy over h omega c is huge parameter, which means that discretization of level is very small, and also what I would like to do, I would like to replace this by integral from 0 to infinity, and this is done through Poisson formula. Fx dx plus what comes x for this 1/24 f prime. So in order to calculate this sum, which contains a lot of numbers, let's estimate how many. As I said, Fermi energy is of the order of 10 to the power 4. H omega c typically is of the order of 1. This is Kelvin. This is Kelvin. So I have to proceed with summation of 10,000 terms in this sum. So when this has to be done, there is a nice way to do it, replacing such big summation by integration and then forcing formula. Well, you can try to do it better, but look, as I said, this is P, which is P1 plus P2. At the same time, this is P1 prime plus P2 prime. So if it is P1, P2, this is P1 prime, P2 prime. So you have integration over dP1 prime dP2, right? So you need to define angles with respect to something. As usual, this is integral, say P1 square dP1 d omega 1 prime dP2 square dP2 d omega 2 prime and here this delta function. This is epsilon P2 prime is P minus P2 squared over 2m. This is P squared over 2m plus P2 squared over 2m plus P2 modulus over m cosine theta, cosine of this angle, right? In your delta function, you have E1 plus E2 minus E1 prime minus this. So this is cosine, cosine what? Cosine theta prime. D omega minus E2 prime. Cosine theta prime. D omega 2. D omega 2 prime is equal to sinus theta 2 prime, d theta prime, d phi prime. So this angle can be integrated out. It gives 2 pi. So this is d cosine theta 2 prime minus. So you see that then you take integration over d cosine 2 prime. So this is this variable. And delta function is removed. So this is how delta function is removed by integration of angle. So you have integral d cosine theta prime, which is x, delta epsilon 1 plus epsilon 2 minus epsilon 1 prime minus p squared over 2m minus p2 squared over 2m plus p2 over m cosine theta 2. So if I replace it by x, this is x, this is x. You see that. So this goes to 1. Yeah. And then this angle just gives you 4 pi. So I did estimation. I didn't calculate coefficients, but this also tells me that as soon as my momentum are in the vicinity of Fermi momentum, in the vicinity of Fermi surface, I replace this by P Fermi square, this by P Fermi square. And doing that more rigorously, I will be able to calculate all coefficients in front of my expression. So this is just
Yes.
Yeah. Sure. Yes, yes. This means you have free motion along z direction. But look, since y coordinate is not explicitly written in the Hamiltonian, you can do this for y2. Only derivative, but there is no y here. Look, let's think about this as ansatz. You assume it, and if you assume it, you come to this equation. It's your guess. No. No. Why should you correlate? Because this is free motion. But let's assume that you have this ansatz. Do you come to any contradiction? No. Because the eigenvalue of y will be put here, and since the coordinate y is not participating in the game, you can you can prove that this function is allowed to depend on x only. There is no any further y. Try to put y, try to put the product, for example, psi x times psi y, and see what the equation for psi y is. Look, as I said, you have a free motion along z direction. And in xy direction, the motion is quantized. So you want to collect all states coming from quantization in xy motion and construct the total number of states. So with z, it's clear that in principle, dn would be d and x, d and y, d and z. With this is clear that this is free motion along this direction. This is d and z is just dpz L3 over 2 pi h. But this one is very much related to your first question. Look, I could have made coordinates x and y symmetric. For example, as I said, I have chosen gauge A is equal to 0 hx 0, which means d over dx, d over dy, d over dz, ex, ey, ez. I put x h. But in principle, I can symmetrize the coordinate. I may write minus yx here and put 1/2. This is also possible. Then coordinates x and y will be symmetric. But since I, in my calculations, use this asymmetric gauge, you see, I put e to the power p y z, e to the power I p y y, which makes you very unhappy. Would I not do it, but using symmetrical, cylindrical gauge, so to say? I will not be able to do that. I will need to use a radial variable. But then I'm saying that everything about x is encoded in Schrödinger equation. While the quantization, this free motion means I need to fix my orbit, namely this x node, to be between 0 and L1. This is only condition which I use. There is no dnx here. All memory about x is encoded in the fact that the centrum of orbit belongs to the box. While in order to collect the state, for x it is degenerate, so to say. This degeneracy comes from the fact of that, and that I collect in states from the plane. But d and y is equal to py dpy L2 over 2 pi h. This means that Cpy over ph is L1 and 0. If I integrate now and calculate all states in the plane, which is integral from 0 to py, from 0 to py here is between 0 and ph over c L1. What I get here is ph over c L1 L2 over 2 pi h. And then I plug it in here, so dn is then equal to not here I integrate over ny. So this is then EH over C, L1, L2, and L3 over 2 pi h square dpz. And you see that this is Bose. Therefore, I have a correct expression. Moreover, the degeneracy itself is proportional to magnetic field. More magnetic field I apply, more states I collect, and this is what is written on this picture. So this magnetic field actually causes the degeneracy. Zero magnetic field will give a zero degeneracy. So then zero state will be accumulated. But finite magnetic field gives me here, and then I need to write the dn over the energy. This is the density of state. This is equal to EH over C, volume over 2 pi h square dpz over the energy. So this expression tells me what's the density of states in the presence of. Because there is no x. I mean, all is due to this asymmetry of my gauge, which I have chosen. Try to use cylindrical gauge, so which says A is 1/2 r times h. This is cylinder gauge, where r is in plane, in xy plane. Sometimes this gauge is also used. Welcome.
No, you should not integrate it. That's the reason. You cannot integrate it. You should not integrate it. But if you want to take the derivative, then you can take the derivative of the integral information. This is the parameter inside the parameter. Because you take the derivative of the key. So you take the derivative here. No, PT you can integrate, but for this one you cannot integrate because it's Gaussian. No, if you put m here, you should integrate over m. If you put m, so you should integrate over m. Because you are putting m here. You have to integrate over this. This should be pn, and this derivative should be dn. If you want to do like this, you should put here d over dn, and this is pn, and integrate over m. If you the relation like this. should put here. Which notation you put here, you should put it here and submit. So the derivative should take over n. And integration should also take over n. Okay.
Hello, good morning.
Good morning.
I don't think Harry.
No, stand for a الحمد لله. كيف الأخبار؟
الحمد لله.
خلاص امتحاناتكم كيف مشت؟
نعم.
امتحاناتك مشت كيف الفاتح؟
والله ما بعرف.
ها؟
والله ما بعرف.
بس اشتغلتي بس ها؟
يعني عملت أكثر من اللي أقدر عليه.
لا تمام.
يا ربي يسهل.
ربنا يسجل
إن شاء الله.
باقي لكم كورس ده صعب صح؟
الميني بادي.
لا الأسئلة انتوا شغالين فيه ده.
الميني بادي.
لا الاسباتاتيك بروسيس انتوا بديتوا المونو بادي؟
إيه.
الليلة؟
لا.
دي صعبة لكن شنو؟
صعبة.
دي صعبة لكن شنو؟
الثالثة ولا.
لكن انا لقيت زول يعني فيها فيزياء يعني، لكن اللي اشتغلت له اسباتاتيك بروسيس ده شغل بتاع ما اعرف امشي خطوتين قدام تعال ده ما بحب.
لكن أنا اشتغلت في السكرتير بروسيس.
قبل كده
لا أنا ما درستها.
عارفاه يعني.
شوية مش كتير، لكن في اللازر انتراكشن مع الاتوم كنت بشتغل بدخل السكان.
يعني انت قاعد فكرة عنها.
فكرة عنها.
تمام.
لكن هي بصراحة
امتحانكم بتاعي
24.
بالتوفيق والمادة دي احنا كم محاضرة عندكم فيها 10 برضه؟
أكتر. لا بسيطة؟
لا المحاضرات انا 12 10 انت 20 30
هي 12 10
مارس
أول شهر يقولنا
لكن صعبة
صعبة
صعبة صعبة
سنة
صعبة
صعبة.
She speak English Arabic Italiano
No, speak
Spanish
Chinese.
good for me. Fine.
Sorry, my